All right, let's get into it. Most of us have been on a plane, right? You're sitting there, sipping your drink, watching a movie, cruising at 35,000 feet. But have you ever stopped to think about what's going on just outside that little window? Out there, it's a completely hostile environment. The air is incredibly thin. There's hardly any oxygen. The temperature is colder than a freezer. If you were suddenly exposed to that environment without protection, you wouldn't be worrying about your connecting flight. You'd have bigger problems, the kind that end your day permanently and quickly. The big villain up there is a lack of pressure, which leads to a condition called hypoxia. That's your body not getting enough oxygen. Our lungs are designed for sea-level pressures. As you go higher, oxygen molecules spread further apart. It's like trying to drink a thick milkshake through a very narrow straw. The consequences are serious: confusion, dizziness, and you can pass out. The magic number, according to the rule makers at the FAA, is around 10,000 feet. Above 12,500 feet, pilots are required to be on supplemental oxygen. So, how do we survive up there? Simple. We cheat. We create a bubble of sea-level-like atmosphere inside a metal tube. The pressurization system takes thin outside air, compresses it, conditions it, and pumps it in. It's the quiet engineering that makes modern air travel possible. So where does all this life-giving pressure come from? It's not magic, and they don't carry it in tanks. The secret is bleed air. Jet engines are phenomenal air compressors. They suck in air and squeeze it through spinning compressor blades. The pressurization system bleeds off a small amount of very hot, highly compressed air before combustion. On a Boeing 737 or an Airbus A320, bleed air is tapped from compressor stages. That raw bleed air runs through the pneumatic and air conditioning packs. First, a heat exchanger chills it using frigid outside air, like a car radiator but far more intense. After cooling, the packs condition temperature and humidity, then vent a steady flow into the cabin. Continuous fresh compressed air inflates the cabin and keeps pressure up. So how do we stop overpressurization? The outflow valve, a computer-controlled door, usually at the back, lets air out to regulate pressure. The system doesn't throttle the incoming air. It modulates how much air exits. A cabin pressure controller opens or closes the outflow valve to hit the target cabin altitude. A little more open, cabin climbs. A little more closed, cabin descends. Typical differential on a 737 is about 8.6 psi. The system won't exceed design limits. Positive relief valves open if differential gets too high. Negative relief prevents outside pressure from exceeding inside during rapid descents. It's a system of checks and balances managing the invisible force that keeps you alive up there. The pressurization system works through every phase of flight: gate, takeoff, cruise, descent. On the ground, the outflow valve is fully open, so cabin pressure equals outside pressure. Before takeoff, the controller pre-pressurizes slightly to smooth the pressure change at rotation. The cabin climbs gradually, typically around 300 to 500 feet per minute, to keep passengers comfortable. The outflow valve closes to trap more air and raise cabin pressure gently. At cruise, say 39,000 feet, the cabin is held near 7,500 feet with tiny outflow adjustments balancing pack airflow. On descent, the valve opens to let more air out, targeting the destination field pressure, often around 300 feet per minute. By touchdown, the pressure differential is zero, so doors can open without a whoosh. For modern jets like the A320 and 737, it's almost entirely automatic. Pilots enter the landing field elevation, and the controller computes the schedule using altitude and vertical speed data. They monitor cabin altitude, cabin vertical speed, differential pressure, outflow valve position, and pack status on ICAS or ECAM. If the cabin climbs too fast or differential nears limits, they'll see amber or red warnings. Manual mode lets pilots command the outflow valve directly. Open to let cabin altitude climb, close to descend, used if automatic controllers fail. Most airliners have two automatic controllers. If the primary fails, the secondary takes over seamlessly. Only if both fail, do pilots go manual. Review. What is the primary role of the pilot in managing pressurization on a modern airliner? What key information is displayed to the pilots? When would a pilot use manual pressurization mode? Why multiple automatic controllers? What happens when the system fails? A loss of cabin pressure is a decompression. Slow decompression, often a leaking seal or malfunctioning controller, creeps cabin altitude up with subtle symptoms. Dangerous because of hypoxia, dizziness, confusion, even euphoria before loss of consciousness. Instruments usually give the first objective warning. Rapid decompression, caused by a sudden breach like a window failure, door failure, or structural damage, creates violent air rush. You'll hear a loud bang, see instant fog, and feel intense wind as loose items fly. The immediate threat is sudden severe hypoxia. Procedures are drilled relentlessly. First action, masks on 100% to keep crew conscious. Next, an emergency descent to about 10,000 feet as quickly and safely as possible. Aloha, 243, 1988. Upper fuselage ripped away. The crew descended and landed. 94 survived, 1 crew member lost. Helios 522, 2005. Pressurization likely misset. Slow hypoxia incapacitated crew. The aircraft flew on autopilot until fuel exhaustion. These are grim reminders why systems, monitoring, and procedures matter. Review. What's the difference between a slow and a rapid decompression? What are the immediate signs of a rapid decompression? What are the first 2 critical actions for pilots? Why are Aloha 243 and Helios 522 important case studies? An aircraft fuselage is a carefully engineered pressure vessel. With over 8 psi differential, each square foot sees more than 1,100 pounds pushing outward. That's like having a small car pressing on every window. Repeated pressurization cycles drive metal fatigue, the chief enemy of aging structures. Cylindrical bodies spread stress evenly, avoiding concentration points. Sharp corners concentrate stress. Rounded windows distribute it and resist fatigue. Specialized aluminum alloys have served for decades. Light, strong, but still susceptible to microscopic crack growth. Newer jets like the 787 use carbon fiber composites. Lighter, stronger, more fatigue-resistant, and corrosion-free, with new inspection needs. Certification involves brutal tests, hydrostatic or full-scale rigs, cycling tens of thousands of pressurization events quickly. Engineers even cut structures to prove damage tolerance, fail-safe design, so that one crack doesn't mean catastrophe. Doors and windows, the weak spots, get special pressure and frame testing. Review. Why are fuselages cylindrical and windows rounded? What is metal fatigue and why worry about it? What advantages do composites bring like on the 787, and what exactly is fail-safe design? A system this critical needs rigorous inspection and maintenance, often overnight in cavernous hangars. Technicians check bleed ducts, pneumatic valves, the outflow valve, and safety relief valves. Meticulous, hands-on work. Non-destructive testing hunts invisible cracks. Eddy current for surface, ultrasonic for deeper flaws, like a CAT scan for airplanes. Door and window seals are critical. They dry, crack, and leak. Inspect, lubricate, and replace immediately to prevent slow decompressions. Ground air carts pressurize the fuselage while technicians verify leaks and valve settings. Review. What key components are checked? What is NDT? Why focus on seals? How is the system tested on the ground? If PSI and bleed air still feel abstract, try a simple analogy. The cabin is a leaky soda bottle. The engines and packs are the pump forcing air in. The small adjustable hole in the cap is the outflow valve. On the ground, it's wide open, pressure equal to outside. As you climb, you close it slightly so inflow exceeds outflow. Pressure builds. At cruise, you tune it so inflow equals outflow. Steady cabin pressure, say 8,000 feet. Close a bit more and cabin altitude descends. Open a bit and it climbs. Safety valves are like pre-scored weak points that pop to dump excess pressure before failure. Review. In this analogy, the pump is engines and packs. The bottle is the cabin. The adjustable hole is the outflow valve, and the weak points are the safety relief valves.